Beyond the familiar planets lies a solar system we are only beginning to map. In that frozen darkness spins a world named Varuna, a distant puzzle in the Kuiper Belt that defies every expectation. By the end of this journey, you will hold the keys to 25 of its deepest secrets, each one a piece of a cosmic detective story that could rewrite what we know about the edge of our own neighborhood. How can a planet-sized object be lighter than a cork? What unseen force keeps it from flying apart as it spins with impossible speed? We are about to sift through the evidence, from its bizarre composition to the tantalizing hints of structures we cannot yet explain. What do you think is the most important question we should be asking about a place like this? The first clue lies not in what we see, but in what we weigh. Varuna's density is a number that simply does not make sense for an object its size. Based on its estimated mass and volume, calculations suggest it is less dense than liquid water. Picture a ball of rock and ice the size of a small country. If you could find an ocean large enough, this entire world would float. For astronomers, that reading is a profound shock. Most objects in the outer solar system, while icy, are still denser than water because they contain a significant rocky core. Varuna seems to be missing that weight. This leads us to two compelling and strange possibilities. The first theory paints Varuna as a cosmic rubble pile, a fragile agglomeration of countless smaller chunks. Its own gravity is too weak to compact these pieces tightly, leaving vast networks of empty spaces and caverns inside. It would be less a solid planet and more a celestial sponge, a fragile structure held together by the barest of touches. The second theory is even more exotic. Perhaps Varuna is not made of the familiar water ice and rock we expect. It could be composed of lighter ices like frozen nitrogen, methane, or carbon monoxide, which are far less dense. These materials are volatile, suggesting a surface that might actively change, sublimating into a tenuous atmosphere when warmed by the distant sun. The impossible density is more than just a curious fact. It is a direct window into this world's violent past and fragile present. A rubble pile structure suggests it formed not from a single collapse of a cloud of material, but from a gentle, slow accumulation of debris after some ancient collision. Its entire being is a monument to a crash that happened billions of years ago. If it is made of exotic ices, it tells a story of a formation location rich in these volatile compounds, a very specific recipe in the early solar system's freezer. Either way, Varuna is not a solid, monolithic world. It is a ghostly, porous, and startlingly delicate place. And if its very fabric is this fragile, it sets the stage for an even more dramatic mystery. How does something so delicate withstand the forces acting upon it? That delicate, porous structure now faces a force that should shatter it. Varuna completes an entire rotation, a full day and night, in roughly 6.3 hours. For perspective, our Earth takes 24 hours. Jupiter, a massive gas giant, spins in just under 10. Yet Varuna, a fragile world possibly held together like a pile of gravel, spins faster than almost any known object of its size. This is not just quick, it is violently, destructively fast. The centrifugal force generated by such a spin should, by all our models, fling material from its equator and tear a loosely bound rubble pile completely apart. So why is Varuna still here? What invisible scaffold is holding this spinning world together against its own desire to fly to pieces? The answer may be locked in its shape. To survive such a whirl, Varuna is almost certainly not a sphere. Think of a pizza chef spinning dough. As it rotates, it flattens and stretches out. For a world as weak and fast as Varuna, the effect would be extreme. Astronomers strongly suspect it is a highly elongated ellipsoid, shaped less like a ball and more like a cosmic football or a giant tumbling potato. This stretched form is a direct concession to the spin, allowing it to find a new, strained equilibrium. but shape alone cannot explain the cohesion. There must be an internal strength, a hidden architecture providing just enough binding force. This could be a network of stronger ice acting like a skeleton within the rubble, or the gentle but persistent grip of its own gravity, just barely sufficient to keep the pieces from escaping their frantic dance. This relentless rotation does more than sculpt its form, it dictates the very experience of its surface. A day on Varuna is a brief, dizzying cycle. The distant sun, little more than a bright star, would race across the sky. Temperatures would swing wildly between the short day and the equally short night, potentially causing surface ices to expand and contract with stressful regularity. Could this driving rhythm create a form of geology? Might it trigger shifts in its fragile crust or drive the slow migration of volatile ices from one side to the other? The spin is not just a statistic, it is the relentless heartbeat of this world, a pulse so rapid it defines every crack, every valley, and every secret the surface holds. And if the surface is this active, what happens when we look for the source of its strange light? That frantic spin may hold the key to another profound silence. Varuna travels its lonely orbit without a known companion. In the distant Kuiper Belt, this solitude is strange. Nearly every other world of comparable size, from Pluto with its family of moons to Haumea with its 2 swift satellites, dances with at least one partner. These binary or multiple systems are the rule, not the exception in that frozen realm. So why is Varuna seemingly alone? Its missing moon is a gap in the expected pattern, a clue written in negative space. One possibility is that Varuna simply formed differently. Perhaps the cloud of material that coalesced into this world was never graced with the right conditions for a smaller partner to form alongside it. It may have been born from a quieter, more isolated process, emerging solo from the primordial disk. A second, more dramatic theory suggests a past filled with violence. Varuna's extreme rotation is a wound from a colossal impact. That same ancient collision that may have created its rubble pile structure could have also been responsible for either destroying a former moon or launching it into the abyss. A grazing blow from another large object could have stolen a companion away, leaving Varuna spinning wounded and alone. The gravitational tides of a close pass with another dwarf planet could have destabilized a moon's orbit, sending it careening off into independent orbit around the sun. Yet there is a third, tantalizing idea. What if we simply have not seen it yet? Varuna is incredibly far and faint. A moon could be hiding in its glare, too close to distinguish with our current telescopes. Or it could be extraordinarily dark, a charcoal black chunk of primordial material that reflects almost no light, making it invisible against the void. It might even be a very small, fast moon, zipping around Varuna so quickly that our occasional snapshots have never caught it at the right moment. The answer, whatever it is a direct record of Varuna's most violent day. A moon would have stabilized its spin, acting as a gravitational brake. Its absence lets that wild rotation continue unchecked. Finding a moon or confirming its lack would tell us whether Varuna's frantic dance is the permanent legacy of a catastrophic birth or a temporary state awaiting a calming influence we have yet to find. This cosmic loneliness shapes everything, including the very light that finally reaches our telescopes. This profound darkness is its own kind of signature. Varuna's surface is a shadow in space, an absorber of light with one of the lowest albedos or reflectivity we have ever measured in the outer solar system. While icy worlds like Pluto or Eris can shine, bouncing back a significant portion of the feeble sunlight that reaches them, Varuna does the opposite. It swallows the light. Imagine the darkest charcoal or the blackest asphalt on a moonless night. That is the visual essence of this distant world, a featureless dark patch that gives almost nothing back to our telescopes. This is not merely a color, it is a profound chemical statement about what coats its surface. The leading suspect is a complex, tar-like substance known as tholins. These are not a single compound, but a thick, gooey sludge of organic molecules created when simple ices like methane and nitrogen are bombarded for eons by cosmic rays and ultraviolet radiation from the sun. It is a process akin to leaving butter on a hot radiator for billions of years, a slow, relentless cooking that transforms clear, volatile ices into a dark, reddish-brown organic gunk. Another possibility is a blanket of carbonaceous soot, similar to the dark material found on some asteroids and moons, perhaps delivered by ancient cometary impacts or formed in place. This incredible darkness is more than a curiosity. It is the primary reason Varuna remains so mysterious. A bright surface would act like a projection screen, revealing craters, plains, and mountains through subtle patterns of light and shadow. Varuna's dark shroud absorbs those details. It is like trying to read a book printed in faint gray ink on black paper under a dim light. Our best images show only a faint, elongated smudge. Every feature, every potential cliff, basin, or crack is hidden beneath this primordial paint. This means we are essentially blind to its geology. We cannot see if it is scarred by ancient impacts, smoothed by glacial flows of exotic ice, or fractured by its rapid spin. The darkness itself becomes the defining characteristic, a cloak that has preserved its secrets in a perfect, lightless vault since the solar system's dawn. What could possibly lift that cloak, even for a moment? Its deep darkness is not a uniform black, but carries a subtle and telling hue. Among the coal-black shadows of the Kuiper Belt, Varuna shows a moderately reddish tint. This is the color conundrum. While many of its distant cousins, like the dwarf planet Sedna, are dramatically red, painted in deep burgundy by eons of radiation cooking their surfaces, Varuna's redness is more muted. It is the difference between old brick and faded terracotta. This color is a direct chemical fingerprint, a clue written in the specific wavelengths of light its dark surface refuses to absorb. The reddening process is a known cosmic recipe. Simple ices like methane, when bombarded by the relentless rain of cosmic rays and solar ultraviolet light over billions of years, slowly transform. They break apart and recombine into those complex, dark organic compounds called tholins, which tend to reflect more red light than blue. The longer the exposure, the deeper and redder the stain becomes. So why is Varuna's stain not as deep? One compelling answer is that its surface might be younger. Imagine a vast glacier of fresh, pale ice slowly oozing across the landscape, covering the ancient, red-stained ground beneath. This could happen through cryovolcanism, where internal warmth pushes slushy ices to the surface, or through the constant churn and refreshment caused by its incredibly fast rotation and extreme temperature swings. A newer surface simply has not had as much time to bake in the cosmic radiation, so its reddening is less advanced. Alternatively, its recipe might be different. Perhaps Varuna's surface holds a different mix of starting ingredients. If it has less methane and more nitrogen or carbon monoxide ice, the resulting tholins would have a different color profile. Or the pervasive dark gunk covering everything might simply be so thick and dominant that it masks the reddish color underneath, presenting a darker, less colorful face to the universe. Compare it to its neighbors. Pluto is famously variegated with vast, bright white plains of nitrogen ice next to dark red highlands. Makemake is brilliantly bright, suggesting very fresh ices. Varuna sits between them, not as colorful as one, not as bright as the other. It is a world with a faded complexion, hinting at either a recent geological event that washed its face or a fundamentally different chemical makeup from its siblings. This single shade of red is a timestamp and an ingredient list, a whisper about the age of its skin and the chemistry of its heart. And if the surface can be refreshed, what does that imply is stirring beneath the frozen crust? That faded red complexion is a surface whisper, but the way its light flickers is a shout. As Varuna spins, its brightness does not pulse with a simple, steady rhythm. Instead, it flickers in a complex pattern, a light curve that tells a story of profound irregularity. A spherical world would show almost no change in brightness as it turns. Varuna's light swings dramatically by as much as 20%. This is the direct signature of a shape that is wildly out of round. Light reflects off a long, mountainous ridge, then dips as a deep valley or a flattened side rotates into view. The pattern is not a clean, repeating sine wave, which suggests the shape is not a simple, elongated football. The variations are complex, hinting at multiple bumps, concavities, or stark contrasts in surface darkness. It is like watching a tumbling, lumpy potato catch the light from a distant lamp, its silhouette constantly shifting against the dark. This erratic dance of light is our primary evidence for its form, and it points to two leading and strange possibilities. The first model is a triaxial ellipsoid. Think of a sphere stretched in 3 different directions by 3 different amounts. It has a long axis, a medium axis, and a short axis, like a potato that has been squashed slightly on one side. This could create the complex light curve as different combinations of these faces rotate toward Earth. The second, even more dramatic model is that Varuna is a contact binary. This would be 2 sizable planetesimals that gently collided and stuck together in the early solar system, creating a distinct peanut or hourglass shape. The light curve could then be explained by the deep valley or neck between the 2 lobes coming in and out of view. Each model carries a different origin story. A triaxial ellipsoid suggests a single body violently stretched by its own rapid spin. A contact binary tells of an ancient, slow-motion merger of 2 separate worlds. For years, the light curve data was all we had, and it supported both ideas. To break the tie, astronomers needed a far more precise measurement, a celestial ruler that could cast a shadow across the solar system. They found it in a stellar occultation. The idea is simple in theory, fiendishly difficult in practice. When Varuna passes directly in front of a distant star, it casts a tiny, precise shadow on Earth. By having multiple telescopes along the predicted shadow path time the exact moment the star winks out and reappears, you can trace the outline of the object. It is like holding a rock up to a single light bulb and studying its silhouette. One such occultation was successfully observed, and the results did not settle the debate, they deepened it. The occultation data suggested a shape that was more spherical than the extreme elongation implied by the light curve. This is the core of the conflict. How can an object that flickers so dramatically also cast a shadow that seems relatively rounded? The answer may lie in what each method measures. The light curve is sensitive to both shape and surface markings. A large, extremely dark region on one hemisphere could cause a major dip in brightness even if the underlying shape is not profoundly irregular. The occultation gives a pure, one-dimensional silhouette at one specific orientation. Combining the clues is like a detective trying to reconstruct a unique statue from a blurry photograph and a single, clean fingerprint. They do not yet match perfectly. So the true shape of Varuna remains in shadow, caught between the story told by its flickering light and the silent testimony of its starry silhouette. Is it a stretched and battered ellipsoid, or 2 ancient worlds forever frozen in a final embrace? The answer defines not just its appearance, but its very origin story. And if its shape is this ambiguous, what does that mean for the stability of the ground beneath an imaginary explorer's feet? This conflict between its flickering light and its star-cast shadow points to a deeper thermodynamic puzzle. The temperature of this dark, distant world is not what our equations say it should be. From the cold, silent data streams of infrared telescopes comes a subtle but persistent anomaly. Varuna appears to be slightly warmer than predicted for an object so far from the Sun. In the absolute zero neighborhood of the Kuiper Belt, even a few degrees of unexpected warmth is a glaring clue. This thermal signature is a whisper of hidden energy, a suggestion that something within or upon this frozen world is actively generating heat. The first and simplest explanation points directly to its charcoal-black complexion. A dark surface is a superb absorber of sunlight. Even the feeble trickle of solar energy that reaches the edge of the solar system can, over time, warm a surface that refuses to reflect it. Think of a black car parked in winter sunlight, its interior growing noticeably warmer than the white car beside it. Varuna's low albedo could be acting exactly like that, soaking up every precious photon and re-radiating the energy as a faint, detectable infrared glow. This is a surface effect, a skin-deep warmth. But what if the heat is coming from within? The second possibility delves into Varuna's hidden heart. Like Earth, it likely contains radioactive elements such as uranium, thorium, and potassium in its rocky component. As these elements decay, they release a slow, steady trickle of heat. This radiogenic heating is the planet's internal battery, a fading remnant of the solar system's violent birth. In a large, dense world, this heat can drive tectonic activity or volcanism. In a fragile rubble pile like Varuna, it might be just enough to maintain a delicate thermal balance, perhaps preventing the deepest interior from plunging to the coldest possible temperatures. It is the gentle, persistent heartbeat of a sleeping world. Then there is the most tantalizing prospect of all, subsurface geothermal activity, fueled not by radioactivity alone, but by a hidden ocean. This is not a wild fantasy. We see its effects on moons like Europa and Enceladus. The constant gravitational tug of war between a moon and its planet generates tidal friction, flexing the interior and creating heat. But Varuna has no large planet nearby and no known moon to create such tides. Could its own rapid, lopsided spin generate enough internal friction to warm its core? Or might an ancient impact have deposited enough energy to melt a reservoir of volatile ices deep below, creating a slushy, briny layer that has taken billions of years to refreeze? The presence of even a relic ocean, now mostly frozen, would act as a vast thermal buffer, releasing warmth slowly over eons and smoothing out the temperature profile we detect from afar. Distinguishing between these sources is the ultimate challenge. Is the warmth a superficial suntan on a dark surface, or the radiating glow of a planet with a still warm heart? The answer reshapes our understanding of what constitutes an active world. It suggests that even in the deepest freeze, far from any star, the fires of formation and decay can still burn, however faintly. If internal heat is real, it could be the engine for the most surprising phenomenon of all, a changing face. That faint, unexpected warmth is a ghost of a story, but to read the full text we need to decipher its light. Spectroscopy is the art of breaking starlight into a rainbow, searching for the unique chemical fingerprints that specific substances leave in the colors they absorb or reflect. For Varuna, this data is infuriatingly sparse, a spectral whisper just at the edge of our hearing. What little we have paints a portrait of profound ambiguity. The expected signature of water ice, the bedrock of most outer solar system worlds, is suspected but weak and unclear. It is as if we are listening for a clear note in a symphony, but hear only a faint, distorted echo. This absence of a clear signal is itself the central clue. The leading suspect for this cosmic censorship is that thick, dark blanket of tholins. Imagine trying to identify the mineral composition of a mountain, but the entire peak is shrouded in a layer of black tar several meters thick. The tar's own complex, messy chemical signature dominates the light, drowning out the subtler whispers of the pure ices it conceals. This tholin coating may be so pervasive and optically thick that it acts as a perfect veil, preventing the true nature of Varuna's icy bedrock from ever reaching our telescopes. So we are left with indirect questions. What volatile ices are actually there, hiding beneath the shroud? On Pluto, we see vast plains of nitrogen ice with patches of methane and carbon monoxide. On Eris, the surface is dominated by methane. Varuna's spectral whisper gives us no such clear answers. Is its surface rich in nitrogen that has been cooked into darkness? Does it possess reservoirs of methane ice that are similarly transformed? Or is its composition something stranger, a mix of more exotic compounds that we have not yet even considered? The critical mystery is one of absence. We do not see the strong, sharp absorption bands of pure methane or nitrogen ice. This could mean those ices are not there in abundance, which would make Varuna chemically distinct from its brighter cousins. Or more likely, it means those ices are present but have been so thoroughly radiation processed into the complex Tholen gunk that their pristine spectral features are completely erased. They are not missing, they are transformed. This spectral ambiguity is more than a technical hurdle. It is the major barrier standing between us and understanding Varuna's true nature. Without a clear chemical inventory, we cannot confidently reconstruct its formation environment in the primordial solar nebula. Was it born closer to the Sun, where certain ices would have evaporated and then migrated out? Or did it form right where it is, from a local recipe that was peculiarly rich in the ingredients for creating this universal darkener? The answer is locked in a light we cannot yet clearly see, a whisper lost in the noise of its own dark skin. And if the surface chemistry is this masked, what does that mean for the possibility of an atmosphere clinging to this swiftly spinning world? The dark shroud that masks its surface also obscures its deepest history, the story of where it was born. Varuna's current orbit is a frozen snapshot, but it is almost certainly not its original home. To understand this world, we must wind the clock back over 4 billion years to the solar system's violent and chaotic youth. The leading theory paints a dramatic picture of gravitational pinball. Varuna likely formed much closer to the Sun, in the dense region of the primordial disk between the orbits of Neptune and Uranus. There, material was plentiful, allowing planetesimals to grow quickly to a substantial size. But this neighborhood was unstable. The newly formed giant planets, especially Neptune, began a slow outward migration. Their immense gravity acted like a cosmic broom, scattering countless objects like Varuna into the distant darkness. This event, known as the Late Heavy Bombardment, was a period of celestial chaos, flinging worlds into the icy expanse we now call the Kuiper Belt. Varuna would have been a refugee, cast out from the warmer, busier inner solar system to the frozen fringe. Its physical properties support this exile story. Its suspected rubble pile structure is exactly what you would expect from a world that suffered a massive collision during this period of violent scattering, a shattered body that only loosely reassembled. The dark, complex tholins on its surface also require a long baking time under the Sun's more intense ultraviolet radiation closer in, before its journey to the dim outskirts. Yet there is a competing, quieter idea. Perhaps Varuna formed right where it is, or very close to it. This in situ formation theory suggests the outer protoplanetary disk was cold and rich enough with ices and dust to coalesce directly into a world of its size. If true, Varuna would be a more pristine relic, a genuine native of the deep freeze rather than a displaced immigrant. Its darker, less reflective surface could then be explained by a different local recipe of ices that simply cook into darker goo, or by a slower, colder accretion process that never formed a dense, compact core. The clue's conflict, its orbit, like those of many Kuiper Belt objects, bears the unmistakable signature of gravitational scattering, a fingerprint of past planetary migration. But its unusual density and possible composition do not perfectly match some of its brighter neighbors, suggesting it might have a different origin story within the belt itself. Was it a refugee from a war zone of colliding giants or a homegrown product of the quiet outer disk? This is not just academic. The answer defines what Varuna truly is. A scattered object tells us about the violence and dynamic rearrangements of our solar system's infancy. A local formation makes it a priceless sample of the raw materials that existed at the very edge of the newborn sun's influence. Its very existence in its current strange state is a testament to that early chaos, a frozen moment from a time when planets were on the move and the fate of worlds was decided by gravitational chance. And if its birthplace is uncertain, the journey it took to get here opens a door to an even grander mystery, one that connects it to a vast, unseen population. The scars of ancient collisions are written in the sky, not just on a world's surface. Across the solar system, we find families of asteroids and dwarf planets, clusters of objects that share strikingly similar orbits and compositions, all born from the catastrophic breakup of a single, larger parent body. The asteroid belt is filled with such families. The dwarf planet Haumea, with its rapid spin and elongated shape, is surrounded by a dozen smaller fragments and even 2 moons, a clear collisional clan. This leads to a pivotal question for our dark, solitary wanderer. Does Varuna have its own scattered family? Is it the surviving patriarch of a cosmic disaster or a lone giant with no kin? Astronomers have scanned the dynamical maps of the Kuiper Belt, searching for other objects whose paths around the Sun closely mirror Varuna's own. A true family would share not just a general neighborhood, but very specific orbital elements, the precise mathematical fingerprints of a common origin. Finding even a few such siblings would be a revelation. It would prove definitively that Varuna was once part of a much larger body that suffered a shattering impact billions of years ago. That event could explain so much: its suspected rubble pile structure, its rapid rotation, even the absence of a large moon. The impact that created a family could have spun it up and stripped any companion away. The search, however, has so far come up empty. No confirmed fragments have been conclusively linked to Varuna. This absence is its own kind of profound clue. Why would such a sizable world, seemingly a perfect candidate for a violent past, appear to have no family? One possibility is that the family exists, but its members are simply too faint and dark to have been detected yet. Varuna's own coal-black complexion suggests its potential fragments would be equally shadowy, vanishing into the background noise of the Kuiper Belt. Our surveys have only scratched the surface of that vast territory. Another, more intriguing idea is that the family was dispersed long ago. The gravitational tides of Neptune over countless slow orbits could have gradually perturbed the fragments, scattering them so widely that their familial connection is no longer obvious from their current path. Their kinship is now hidden in plain sight, lost in the crowd. Or perhaps the formative impact was of a different kind, a gentler merger or a grazing collision that created Varuna's strange shape without generating a large cloud of debris. It might be a contact binary born from a slow embrace, not a shattering explosion. The ongoing search for its kin is more than a celestial census. It is a forensic investigation into a possible murder that created the world we see today. Every new, dark object discovered in the distant belt is now a potential suspect, a piece of a puzzle that could, with the right orbital calculations, snap into place beside its silent, spinning parent. Until we find them, Varuna's violent birth remains an unconfirmed theory, and its solitude in the dark feels even more profound. Beneath that dark, unyielding crust lies the greatest unknown of all, the hidden architecture of Varuna's interior. We have clues from its impossible lightness and frantic spin, but they point in contradictory directions, forcing us to imagine 2 radically different worlds beneath the same frozen skin. The first model is one of order and separation. If Varuna is differentiated, it would possess a dense, rocky core at its center, wrapped in a thick mantle of water ice and topped by that dark, organic, rich crust. This is the classic planetary structure, like a cosmic jawbreaker, with layers sorted by density during a hot, active formation. The heat from radioactive decay in the rocks could have been enough, long ago, to melt the surrounding ices, allowing the heavy material to sink and the light material to rise. This process would leave behind a world with a clear internal history, a place that experienced a fiery youth. The alternative is a portrait of primitive chaos. Varuna could be a homogeneous mix, a primordial stew of rock and ice chunks all jumbled together from its surface to its very center. This undifferentiated structure suggests it never experienced significant internal heating. It is a fossil, a snapshot of the raw materials that came together in the cold outer disk, preserved in their original, scrambled state. This model fits perfectly with the idea of a fragile rubble pile, its pieces never compacted or cooked enough to separate. The evidence from its density tantalizingly supports both ideas. A differentiated body with a rocky core should be denser than what we measure. Yet, a homogeneous mix of ice and rock would also be denser than Varuna appears to be. This is the crux of the enigma. Its astonishing lightness forces us to consider vast voids and caverns within either structure, a Swiss cheese world regardless of its composition. But within that porous, icy mantle, a third and breathtaking possibility emerges. Could there be a pocket of liquid surviving in the deep freeze? On moons like Enceladus and Europa, subsurface oceans are kept liquid by tidal friction from their giant planets. Varuna has no such gravitational partner, yet its own radiogenic heat, trapped by an insulating blanket of ice and porous rock, might be enough to maintain a localized slushy layer. The presence of antifreeze compounds like ammonia mixed into the water ice could dramatically lower its freezing point, allowing a briny, alien sea to persist for billions of years. This is not a global, churning ocean, but perhaps a deep, isolated aquifer, a dark, salty lake sealed in absolute darkness. The implications of this internal mystery are profound. A differentiated structure with a rocky core suggests past geological activity, perhaps even ancient cryovolcanism that helped shape the crust and vented volatiles to the surface. A homogeneous, primitive interior means Varuna is a static, dead relic, its surface features shaped almost entirely by external impacts and its mad spin. And a subsurface ocean, however small, transforms it from a frozen corpse into a potentially active world, a place where chemistry and heat could interact in ways that, while almost certainly not biological, are far more complex than we ever imagined for such a distant object. The truth is locked away under miles of ice and darkness, waiting for a signal we do not yet know how to send. A hidden ocean is a profound secret, but a fleeting sky would be a visible ghost. The possibility of a temporary atmosphere around Varuna is a whisper of a world that breathes, however faintly. Most of its long, elliptical orbit is spent in a deep, airless freeze, too cold for any gas to remain unbound. But when it makes its closest approach to the Sun, a point called perihelion, everything changes. For a brief cosmic season, lasting perhaps just decades or centuries, sunlight grows marginally stronger. On a surface suspected to hold volatile ices like nitrogen, methane, or carbon monoxide, that slight warmth could be enough. These frozen gases would not melt, they would sublimate, transforming directly from solid ice into a thin, escaping vapor. In that moment, Varuna could wake from its frozen slumber and exhale a temporary sky. This atmosphere would be unimaginably tenuous, a wisp of gas far thinner than the air on Mars, more akin to the coma of a comet than the robust blanket of a planet. Its composition would be a direct readout of the surface ices finally getting a chance to escape. The primary component would likely be nitrogen, a gas that dominates the atmospheres of Pluto and Triton. Mixed in would be methane and possibly carbon monoxide, along with traces of noble gases like argon, baked out of the ancient rocks within. But this would not be a clean, simple air. That pervasive layer of dark tholins coating the surface would complicate everything. As the ices sublimated, they would likely carry aloft fine particles of this organic haze, creating a smoggy, reddish shroud that could actually help stabilize the atmosphere by absorbing sunlight and providing extra warmth. The life of this phantom atmosphere would be a frantic, doomed cycle. Varuna's incredibly weak gravity, only a fraction of our moon's, would struggle to hold onto these fast-moving gas molecules. The atmosphere would be in a constant state of escape, streaming away into space like a slow, invisible solar wind. To persist at all, the rate of sublimation from the warming surface would have to outpace this relentless loss. This creates a dynamic, flickering envelope, possibly patchy and localized over the sunniest regions, especially if Varuna's dark and bright patches are uneven. Then, as its orbit carries it back into the profound cold of the outer belt, the process reverses, the temperature plummets, the tenuous gases no longer have the energy to stay aloft. They freeze directly back onto the surface, falling as a frost of fresh, pristine ice, perhaps in different locations than they started, painting new patterns on the dark ground. This seasonal deposition could be the mechanism that partially refreshes Varuna's face, covering older, redder tholins with a bright frost that then itself slowly darkens over the millennia until the next close approach. It is a world that periodically changes its own close, a slow-motion cycle of exhalation and frosty silence. If this phantom is real, its brief appearance would solve one mystery while creating another, for it would require a surface far more active and volatile than its dark visage suggests. That phantom atmosphere would require a source, a reservoir of volatile ices that could be mobilized by the faintest whisper of warmth. This brings us to a dramatic possibility hidden beneath the crust. Could Varuna have its own form of volcanism? Not the fiery, molten rock of Earth, but the cold, slow eruption of icy slush, a phenomenon we call cryovolcanism. The recipe seems improbable here. We lack the clear surface features, the smooth plains or distinctive domes we see on worlds like Pluto or Ceres. Yet, the fundamental ingredients for this frozen geology might still be present, waiting for the right conditions to stir. The first ingredient is internal heat. We suspect Varuna is slightly warmer than it should be. That warmth, whether from radioactive decay or the lingering energy of its formation, could be just enough to soften the icy mixture deep within its porous interior. The second ingredient is a volatile substance with a low melting point. Water ice alone is too hard, but mix it with ammonia or salts, common antifreeze compounds in the outer solar system, and its freezing point plummets. This creates a briny, slushy fluid that can ooze under pressure. The final ingredient is a driving force. On Saturn's moon Enceladus, the gravitational squeeze from the giant planet provides that force, flexing the interior and powering spectacular geysers that jet into space. Varuna has no such planetary partner, but its own rapid, lopsided spin could generate internal friction, a constant, gentle churning that builds pressure in pockets of slush. So what might cryovolcanism look like on this dark, distant world? It would not be a towering, fiery spectacle. More likely, it would be a slow, viscous ooze. Imagine a glacier of ammonia-rich water ice, not creeping over bedrock, but slowly welling up from a fissure caused by the stresses of its wild rotation. This slush would spread across the dark terrain, a bright, fresh stain against the ancient tholin blanket, before eventually freezing solid into a new, icy plain. Alternatively, if the pressure built sufficiently, more dramatic eruptions could occur. Trapped gases within the slush could expand explosively as it reached the near vacuum at the surface, creating geysers that might shoot jets of icy crystals and vapor a short distance into the sky before they fell back as a fine, bright snow. We see this on Neptune's moon Triton, where nitrogen geysers erupt under the distant sun's weak warmth. For Varuna, the trigger might not be sunlight, but a periodic buildup of stress from its spin or the occasional shudder from a distant impact. The evidence, however, remains stubbornly absent. Our blurry images show no obvious cryovolcanic constructs, but consider the perfect camouflage. Any fresh, bright ice erupted onto Varuna's surface would be a target. The relentless bombardment of cosmic rays and solar radiation would begin cooking it immediately, transforming that pristine slush into the same dark, reddish-brown tholin gunk that covers everything else. A cryovolcanic flow from 1 million years ago might now be utterly indistinguishable from the surrounding terrain, its origins buried under a chemical stain. This means Varuna could have an active or recently active geological heart, and we would never know by looking at its uniformly dark face. The potential for such cold, slow eruptions forces us to reconsider what activity means in the deep freeze. It suggests a world not frozen in time, but one with a slow, patient pulse, where geology operates on timescales of eons, and change is measured not in lava flows, but in the gradual seepage of alien antifreeze into the eternal night. If the interior can ooze to the surface, what does that imply about the forces that could tear it apart from the outside? The potential for hidden eruptions speaks of a world with a slow, patient pulse, but its true value may lie in its profound stillness. Varuna is not just an active puzzle, it is a cosmic vault, a deep freeze time capsule sealed at the dawn of our solar system. For 4.5 billion years, it has hung in that distant, silent cold, a place where time itself seems to have slowed to a near standstill. This environment is a perfect preservative. On Earth, geological activity, water, and wind constantly recycle and erase the ancient past. On warmer, active worlds, internal heat churns and renews the surface. But in the absolute freeze of the Kuiper Belt, chemical and physical processes that would take millennia closer to the Sun might require eons. Varuna's interior, whether a primitive jumble or a layered structure, has likely been in a state of deep hibernation since its formation. This means the materials that came together to build it, the very ice and dust grains from the protoplanetary disk that swirled around our infant sun, could remain almost perfectly unchanged. It is like finding a sealed jar of ingredients from the very first meal ever prepared in your kitchen, with every spice and grain exactly as it was on day one. The mystery locked within this vault is the precise recipe of our solar system's birth. What was the exact mix of ices and silicates in this region of space? Did the disk have a smooth gradient of materials, or was it patchy with zones of different chemistry? Varuna's composition, if we could ever sample it directly, would provide a data point frozen in time. The ratios of different isotopes in its water ice, for instance, are a thermometer and a clock. They can tell us the temperature of the cloud of gas and dust it formed from, and even hint at whether that water was made in the cold outer disk or was transported outward from closer to the sun. The types of organic tholins on its surface are not just a dark stain. They are a record of the intensity and duration of radiation bombardment in the early solar system, a measure of how long it basked in a younger, more active sun's ultraviolet glow before being scattered to the fringe. Studying Varuna is not merely about understanding one strange world. It is about using that world as a singular reference book to decode the conditions of our entire cosmic neighborhood's infancy. Its very existence offers a control sample, a piece of untouched evidence against which we can compare everything else from the planets to the comets. It holds the unedited first draft of our solar system story, written in ice and rock and preserved in the perfect cold of deep space. To open this time capsule would be to read a chapter of history we have only ever been able to imagine. The profound stillness of that cosmic vault carries a name with ancient echoes. This distant world is not called Varuna by accident. Its name was drawn from the deep well of human mythology, specifically the pantheon of Hindu tradition. In those ancient stories, Varuna is a powerful and complex deity, the god of the sky, the oceans, and most significantly, the keeper of Rita, the cosmic order, the divine law that governs the universe. He is the celestial sovereign who ensures the sun rises, the seasons turn, and the moral fabric of reality remains intact. There is a profound and playful poetry in linking this mythological figure to our enigmatic Kuiper Belt object. We sent our telescopes into the heavens searching for order, for predictable patterns in the orbits of planets. Instead, in the darkness, we found this namesake world that seems to defy the very laws we expected to govern it. So we must ask, is the cosmic Varuna acting as its divine namesake, dutifully keeping a physical law we do not yet understand? Or is it the celestial rebel, quietly breaking the rules we thought were universal? Consider its impossible lightness, its frantic spin that should tear it apart, its contradictory shape. From our current perspective, it appears to be a rule breaker, an outlier that challenges our textbooks. But mythology offers a different lens. The god Varuna was not just about rigid order, he was also associated with the hidden, the mysterious depths of the night sky and the unseen ocean floor. He knew secrets beyond mortal comprehension. In that sense, our Varuna is perfectly named. It is not breaking laws, it is operating under a deeper, more subtle set of cosmic principles that we have not yet fully deciphered. Its mysteries are not errors, they are clues to a more complete understanding of physics at the edge of our solar system. The ancient storytellers looked up and saw divine order in the celestial dance. We look at Varuna and see a puzzle. Perhaps both views are converging on the same truth, that what appears as chaos is merely a more complex form of order, waiting for its law to be read. This bridge from myth to science reminds us that our quest to understand the universe is a timeless human story, one that begins with wonder at the stars and continues with the patient decoding of their light. And if this world is a keeper of deeper laws, what other fundamental truths might its orbit around the sun be trying to show us? The deeper laws Varuna might obey are hidden by a more basic uncertainty. We cannot say for sure how big it is. This is the size-ranking riddle, a fundamental debate that changes how we see this world's place in the cosmic lineup. In the early 2000s, initial observations painted Varuna as a giant. Its brightness, combined with an assumed reflectivity similar to other icy objects, suggested a diameter approaching 900 kilometers. That would have placed it firmly among the top contenders in the Kuiper Belt, a true planetary heavyweight on the fringe. But then came the sharper tools, the stellar occultations. By timing the precise moment Varuna passed in front of a distant star, astronomers could trace its silhouette with far greater accuracy than brightness alone could ever allow. Those results were a shock. The occultation data pointed to a much smaller figure, around 670 kilometers in diameter. That is a staggering discrepancy of over 200 kilometers, a difference wider than many countries. So which number is right, and why does it matter so profoundly? The core of the problem is Varuna's darkness. Measuring a distant object's size with light alone is a two-step guess. First, you measure how much sunlight it reflects. Then, you have to assume how reflective its surface is to calculate the area needed to bounce back that much light. It is like trying to judge the size of a car at night by its headlights, but not knowing if the headlights are dim halogen bulbs or blinding LEDs. Early estimates assumed Varuna had a moderately bright, icy surface, which required a large area to produce the faint glow we saw. But we now know its surface is among the darkest in the solar system, a cosmic black hole for light. A dark surface absorbs most light, so to appear as bright as it does, Varuna does not need to be as large. It simply needs to be a little less dark and a little smaller. The occultation cuts through this guesswork by giving a direct physical measurement, a shadow's edge. The smaller size from occultations paired with its known mass is what gives us that impossibly low density. If the older, larger size were correct, its density would be even more bafflingly low, defying all known physics for a world of that scale. This uncertainty ripples through every classification. Is Varuna among the 10 largest known trans-Neptunian objects, or does it sit further down the list? Its ranking changes depending on which measurement you trust, altering its perceived importance in the grand architecture of the Kuiper Belt. This is not just academic bookkeeping, it influences which missions get proposed, which worlds are deemed worthy of deeper study, and how we model the formation of the solar system's third zone. The size riddle is a humbling reminder that at the very edge of our vision, even the most basic facts remain slippery, defined as much by what we do not know as by what we do. And if we cannot pin down its dimensions, how can we hope to understand the subtle forces that might be actively reshaping it? Its precise dimensions may be unknown, but the true face of Varuna is a map we cannot read. If we could fly a spacecraft close enough to map its entire surface, what would we actually see? The assumption is a uniform, featureless blackness, a charcoal ball against the stars. But nature rarely creates perfect uniformity. The first and most likely break in the darkness would be fresh impact craters. Imagine a small, wandering Kuiper Belt object, a cosmic pebble, striking Varuna's surface at tremendous speed. The impact would blast away the ancient dark Tholen blanket, excavating a bowl of material from beneath. That freshly exposed subsurface could be dramatically different. It might be bright water-ice bedrock or a layer of paler, less processed volatile ices. For a brief geological moment, that crater would gleam like a white scar on a black hide, a pinprick of light in the abyss. But it would not last. The relentless radiation bath would begin its work immediately, cooking the fresh ice into new tholins. Within perhaps 1,000,000 years, the scar would fade to gray, then to the same inky black as its surroundings. A global map might therefore be a record of recent violence, dotted with the faint, fading ghosts of the youngest craters, their edges slowly being consumed by the creeping dark. Beyond impacts, Varuna's own frantic rhythm could paint patterns we can scarcely predict. Its 6-hour day creates a wild temperature swing. The side facing the distant sun might warm just enough, perhaps only a few degrees, to cause the sublimation of the most volatile frosts like nitrogen or methane. These gases could then drift across the terminator, the line between day and night, and refreeze on the colder, dark side. This process, called frost migration, could create a subtle, shifting pattern of bright frost patches in the permanent shadow of craters at the poles or along the trailing edge of the night side. It would be a whisper of contrast, a faint zebra stripe of frost and shadow driven by its dizzying spin. The map might also reveal the hand of its suspected shape. If Varuna is a contact binary, the deep neck or valley between its two lobes could be a permanent shadow zone, a cold trap where volatile ices accumulate over eons into a permanent, bright frost deposit. If it is a stretched ellipsoid, the gravitational field would be weaker at the elongated ends, potentially affecting where surface materials slide and settle. We might see dark material pooled in the low-gravity regions and brighter, more stable bedrock at the poles. The greatest mystery a map could solve is the presence of active geology. A single, surprising feature would change everything. A long, linear fissure could hint at tectonic cracking from its rapid rotation or past tidal stresses. A smooth, flat plain, even a small one, would be a screaming indicator of cryovolcanic resurfacing, a place where slushy ice once oozed out and froze into a new layer. A cluster of pit chains or collapsed depressions could point to subsurface voids, the caverns within its rubble pile structure caving in. But from here, with our telescopes, we see none of it. We are trying to discern the texture of a mountain from a silhouette seen 1,000 miles away in a fog. The absence of data is not evidence of absence, it is simply a blank page. Varuna's albedo map is a canvas waiting for the first stroke of light, a global story written in shades of black we have not yet learned to see. And if its surface is this cryptic, what does that imply about the very space it moves through and the shadows that might be following it? That blank, black canvas is almost certainly not smooth. Every solid world in the solar system that lacks a protective atmosphere carries a history written in craters, a guest book signed by countless collisions over billions of years. The Moon, Mercury, the asteroids, they all bear this pockmarked testament to a violent past. So what scars does Varuna hold? The answer is a profound unknown, a mystery hidden by its own darkness. We cannot see a single crater, but we can reason about what must be there. If its surface is truly ancient, dating back 4.5 billion years to the solar system's chaotic youth, it should be saturated with impact scars. The early Kuiper Belt was a crowded shooting gallery filled with leftover planetesimals. A surface from that era would look like the Moon's highlands, a landscape so densely cratered that new impacts erase old ones. That would make Varuna a priceless historical archive. By studying the size and distribution of those unseen craters, we could reconstruct the population of small objects in the primordial Kuiper Belt, learning what sizes of debris were most common as the planets finished forming. It would give us a statistical portrait of the construction materials left over at the edge of our system. But there is a compelling alternative, a reason why that cratered record might be faint or even missing entirely. Perhaps Varuna's surface is not ancient but surprisingly young. Something could have erased the craters, wiping the slate clean long after the heavy bombardment ended. What force could do that on a frozen, airless world? One possibility is that phantom atmosphere we considered. If, during its closer approaches to the Sun, volatile ices sublimate into a temporary gas envelope, the process would not be gentle. The escaping gases could carry with them fine dust and debris, slowly sandblasting the surface over millions of seasonal cycles. This atmospheric sanding could soften crater rims, fill in basins, and gradually smooth the terrain, like wind slowly erasing footprints in a desert. Another, more dramatic eraser is internal activity. If cryovolcanism is real, even as a slow, viscous ooze, fresh flows of icy slush could have resurfaced vast areas, burying ancient craters under a new, blank layer of ice. This ice would then darken over time, hiding the renewal beneath the familiar Tholen stain. Even its rapid spin could play a role. The extreme temperature swings between its short day and night could cause the surface ices to expand and contract with tremendous stress, triggering global-scale cracking and gradual tectonic shifts that over eons rearrange the landscape like the slow shifting of pack ice on a polar sea. So the crater count, or lack thereof, is a direct clock. A heavily cratered Varuna is a passive relic, a silent witness to early violence. A smooth Varuna is an active world, one with a geological heartbeat that renews its face. Our inability to see which it is creates a tantalizing fork in the road of understanding. Either this dark world is the solar system's most pristine history book, its pages unread, or it is a world with secrets still stirring beneath the ink-black cover. The idea that Varuna might be two worlds in one is not just a shape, it is an origin story. The contact binary theory proposes that we are not looking at a single, stretched object, but at the final, frozen embrace of two separate planetesimals that drifted together and gently merged billions of years ago. This slow-motion cosmic kiss would have created a distinct peanut or hourglass shape, a world with a deep valley or a pinched waist where the two lobes meet. This model elegantly explains several of our deepest puzzles. That wildly complex light curve with its erratic flickers could be the result of the deep cleft between the two bodies rotating in and out of view, casting long shadows and presenting wildly different profiles. Its rapid rotation could be the inherited spin from that ancient, gentle collision, a final pirouette locked in as the two bodies became one, and most compellingly, it could solve the mystery of the missing moon. If Varuna formed this way, it never had a separate satellite to begin with. It is its own binary system, permanently fused. The evidence for this idea comes primarily from that challenging light curve data. Computer models that try to recreate Varuna's specific pattern of brightness changes often find that a contact binary shape provides a better fit than a simple, stretched ellipsoid. The variations are simply too sharp and irregular to be easily explained by a single, lumpy body. Furthermore, we see this architecture elsewhere in the Kuiper Belt. The most famous example is Arakoth, the snowman-shaped world visited by the New Horizons spacecraft. Its two distinct connected lobes are a pristine fossil of exactly this kind of gentle merger, proving the process happened in the cold outer disk. If it happened to Arakoth, why not to Varuna? Yet, the theory faces a significant counterargument: the stellar occultation. When Varuna passed in front of that star, the silhouetted cast was more rounded than the extreme hourglass shape a classic contact binary would predict. The shadow did not show a dramatic dip or indentation at the waist. Proponents of the binary model have a rebuttal. They suggest the occultation might have occurred across a more uniform part of one of the lobes, missing the deep neck entirely. Or, over billions of years, the gravitational pull between the two merged bodies could have slowly deformed and smoothed their junction, filling in the valley with debris and ice, creating a smoother profile while the underlying two-part structure remained. The alternative, of course, is that Varuna is a single, coherent world, a triaxial ellipsoid stretched thin by its own centrifugal force. This model requires no special merger event, just the natural consequence of a fragile object spinning too fast for its own good. The debate between these two theories is not merely about shape, it is about the very nature of the early Kuiper Belt. Was it a place of quiet, slow dances where worlds gently coalesced through low-speed mergers, or a violent arena where single bodies were spun up and shattered by catastrophic impacts? The answer lies in the silent geometry of a dark shape tumbling in the void, a geometry we have not yet fully traced. The shape of Varuna may be a question of two bodies or one, but its path through the void is a matter of precise celestial clockwork. It is locked in a gravitational dance with the solar system's outermost giant, a rhythmic pattern known as an orbital resonance. For every 2 laps Neptune completes around the Sun, Varuna completes exactly 3. This is not a random ratio, it is a 3-2 resonance, a stable, repeating gravitational conversation that prevents the two worlds from ever coming too close. This same exact rhythm is the heartbeat of Pluto's orbit. The coincidence is too perfect to ignore. How did two such different worlds, one a bright, complex king of the Kuiper Belt and the other a dark, solitary mystery, end up marching to the exact same cosmic drumbeat? This resonance is a powerful stabilizing force. Think of pushing a child on a swing. If you push at just the right moment in the arc, you reinforce the motion, making it stronger and more stable. Neptune's gravity gives Varuna a similar, perfectly timed tug at specific points in its elongated orbit, ensuring their paths never intersect and preventing a catastrophic close encounter that would fling the smaller world into the abyss. It is a celestial safety net woven by gravity itself, but this safety net also tells a story of a violent past. Varuna almost certainly did not form in this resonant lock. It was captured. The leading theory paints a picture of the solar system's chaotic youth when Neptune migrated outward into the primordial disk of icy debris. As the giant planet moved, its immense gravity swept up countless objects like Varuna, tossing them into new orbits. Some were ejected entirely, some were sent into the scattered disk, and a fortunate few, at just the right distance and speed, were gently nudged into these stable resonant patterns. The 3-2 resonance is a particularly strong and common one, a gravitational sweet spot. So, does sharing this rhythm with Pluto mean they are long-lost siblings from the same ancient neighborhood? It is a compelling clue, but not definitive proof. They could be refugees from the same broad region of space that Neptune swept through, captured by the same process during the same epoch of planetary migration. They share a dynamical family, a group of objects called Plutinos, all trapped in this 3-2 dance with Neptune. But membership in the same club does not guarantee an identical origin story. Pluto and Varuna could have formed in slightly different parts of the protoplanetary disk with different compositions, and then been herded into the same orbital pen by Neptune's gravitational fence. Their profound physical differences, one bright and complex, the other dark and seemingly simple, suggest they may be very different kinds of objects that simply ended up on the same gravitational highway. Yet, the resonance is a powerful constraint. It tells us that whatever their origins, both worlds have been following this precise, protected path for billions of years, a shared history written not in rock or ice, but in the silent mathematics of motion. This stable lock has preserved them, allowing us to find them today. It is the reason Varuna is still there for us to puzzle over, a dark note held in a perfect, endless chord with a distant giant. A year on Varuna is a measure of deep time itself. This world completes a single orbit around the Sun not in months, but over a span of 283 Earth years. To grasp that scale, consider that the last time Varuna was at the point in its orbit where it is now, the concept of the United States of America did not yet exist. Its seasons are not measured in months, but in human lifetimes, in the rise and fall of civilizations. This glacial orbital rhythm creates a climate cycle of almost unimaginable patience and extremity. For over a century at a time, Varuna slowly drifts inward toward its closest approach to the Sun, its perihelion. The distant star grows from a piercing bright point to a slightly less distant piercing bright point. The difference in solar energy is minuscule by our standards, but in the hypersensitive freeze of the Kuiper Belt, it is a monumental shift. Surface temperatures, currently hovering near absolute zero at about -230 degrees Celsius, might climb by perhaps 20 or 30 degrees during this long, slow summer. That is the difference between an unimaginable cold and a merely impossible one. But for volatile ices, it is the difference between being frozen solid and having just enough energy to leap into space. Then, for the next century and a half, the long winter retreat begins. Varuna slides back into the profound outer dark to its aphelion. The sun shrinks further, the trickle of heat diminishes to nearly nothing, and the world plunges back into a deeper, more permanent freeze. This multi-century cycle is the master clock for every process on or near Varuna. It is the likely engine for that phantom atmosphere. During the decades surrounding perihelion, the slight warming could trigger the sublimation of surface ices, allowing Varuna to exhale its thin, temporary sky. For a human observer, this would not be a sudden spring, but a change so gradual it would be imperceptible across generations. The atmosphere would thicken for decades, persist for maybe a century, and then, over another long century, slowly freeze back onto the surface as the great winter returns. The frost would not necessarily fall where it started. Prevailing solar winds and the world's own rapid spin could deposit it in new patterns, creating bright polar caps or frost-filled craters that last for millennia before the next summer thaw. This raises a profound question about climate. Could there be a lag, a thermal memory buried in its crust? The heat from a closer approach might take decades to penetrate just a few meters into the icy, porous surface. By the time the interior warms up, Varuna might already be on its way back toward aphelion, creating a delayed reaction that smooths out the temperature extremes. Or the deposition of bright frost during the freezing phase could increase the surface reflectivity, causing the next summer to be slightly cooler, a feedback loop that moderates the cycle. The seasonal extremes are not merely a curiosity of orbital mechanics. They are the slow, relentless heartbeat that may give this dark world a form of life, not biological but geological. It is a world that breathes once every 3 centuries, a sleeping giant whose dreams of activity are measured in epochs we can hardly comprehend. That slow, deep breath of its orbital seasons is met by a relentless, microscopic rain. While its climate shifts over centuries, the surface of Varuna endures a constant, invisible storm. This is space weathering, the slow-motion sandblasting of deep space, and it is the artist that painted this world black. The process is deceptively simple in its brutality. For over 4 billion years, Varuna has been exposed, unprotected by any magnetic field or thick atmosphere. Two primary forces are at work. The first is the solar wind, a supersonic stream of charged particles, mostly protons and electrons, constantly flowing from the sun. Even at Varuna's vast distance, this wind is a persistent, etching spray. The second, more powerful force is galactic cosmic rays, high-energy atomic nuclei shot from distant supernova across the galaxy. These particles strike with tremendous force like microscopic bullets. They do not just hit the surface, they penetrate it, breaking molecular bonds deep within the icy matrix. Imagine leaving a complex plastic toy outside in the sun for decades. The ultraviolet light makes it brittle, fades its color, and changes its very chemistry. Space weathering is that process, but amplified to nuclear levels and operating over timescales longer than human history. On Varuna, the primary targets are the simple ices thought to be in its crust, like frozen methane, nitrogen, and water. A cosmic ray slams into a methane molecule, shattering it into fragments, carbon and hydrogen. These radicals are highly reactive, and they immediately scramble to recombine with whatever is nearby. They link up with other broken fragments, with nitrogen atoms, with any stray oxygen. Through countless trillions of these random high-energy collisions, they build increasingly complex and heavy organic molecules. The end product is that thick, tarry sludge we call tholins. This is not a single substance, but a vast family of dark, reddish-brown, carbon-rich gunk. The mystery is one of depth and finality. Has this process completely transformed Varuna's skin? Is the dark red material we see just a relatively thin veneer, a sunburn on a world that is fundamentally bright and icy beneath? Or has the weathering penetrated so deeply over so many eons that the entire outer shell of the planet, down to hundreds of meters, is now this primordial organic tar? The answer reshapes what we think this world is made of. If the coating is thin, then a fresh impact crater or a landslide could expose a glittering underworld of pure, pale ice, a stark contrast hidden just beneath the soot. If the weathering is pervasive, then Varuna is fundamentally a dark world, through and through, its original icy composition now forever lost to chemistry. This also acts as a perfect camouflage. A young, bright surface feature like a cryovolcanic flow or a recent impact scar would stand out brilliantly at first. But space weathering begins its work immediately. Within 1,000,000 years, that bright white patch would turn gray, then reddish, and finally blend into the uniform blackness of the ancient terrain. Any recent geological activity could be completely invisible to us, its evidence already chemically erased. So when we look at Varuna, we are not seeing its true face. We are seeing the oldest, most irradiated layer, the outermost rind of a 4 billion-year-old fossil. The original colors, the fresh ice, the clear chemical signatures of its birth are all buried under this universal darkener. It is like trying to judge the condition of a ship's hull by looking only at the thick, ancient barnacles covering it. To know what lies beneath, we would need to somehow scrape those barnacles away, to peer past the endless storm and see the surface as it was meant to be seen. Scraping away that ancient, irradiated rind is a task for a machine we have not yet built, a spacecraft that has not yet launched. While no mission to Varuna is on any agency's drawing board, its profound collection of mysteries makes it one of the most compelling hypothetical destinations at the edge of our solar system. A flyby mission, a swift visitor like New Horizons but targeted at this dark enigma, would be a voyage designed to answer questions we can only guess at today. Its primary goal would be to resolve the fundamental contradictions that define our current view. The first and most dramatic revelation would come from a single, crisp image. A camera pointing back at the departing spacecraft would capture Varuna silhouetted against the sun, providing an unambiguous, direct measurement of its true shape. Is it a stretched ellipsoid or a contact binary? That one picture would end the debate that has lasted for decades. telling us in an instant whether this world is a single, misshapen body or the frozen merger of two ancient progenitors. As the probe raced past, its other instruments would come alive. A suite of spectrometers would finally cut through the Tholen veil, bathing the surface in different wavelengths of light to detect the specific chemical fingerprints of the ices hiding underneath. We would learn definitively if methane, nitrogen, or carbon monoxide are present and in what ratios. This data would solve the composition mystery, revealing whether Varuna is chemically akin to Pluto or something entirely unique. A sensitive radioscience experiment would use the spacecraft's signal to probe the world's gravity field. By tracking how Varuna's pull subtly altered the probe's path, scientists could map the distribution of mass inside. Does it have a dense, rocky core, or is it a homogeneous jumble? The data could even hint at those vast internal caverns or the possible presence of a subsurface ocean, detecting anomalies in the gravitational tug. The search for a transient atmosphere would involve looking for a telltale glow of sunlight scattering off gas molecules, or for the way radio signals might bend as they passed through even the thinnest of vapors. And all the while, the cameras would be scanning the surrounding darkness, looking for the faint, reflective glint of any hidden moons, no matter how small or dark, finally answering the question of Varuna's cosmic solitude. But the most breathtaking return would be the surface map. As the spacecraft approached, the featureless black smudge would resolve into a real landscape. We would see for the first time whether that dark canvas is cratered, smooth, or cracked. We might spot bright frost deposits in polar shadows, evidence of frost migration driven by its rapid spin. Long linear fractures could testify to tectonic stresses. Most hoped for would be a single, unambiguous cryovolcanic feature, a dome or a flow, proving this dark world has a geological pulse. Every pixel of that map would transform Varuna from a set of conflicting numbers and theories into a place, a world with a history written in ice and shadow. The data from such a flyby would not just solve 24 mysteries, it would provide the foundational context for understanding the entire diverse population of the Kuiper Belt. Varuna represents a missing puzzle piece, a dark counterpart to the brighter, better-known worlds. By studying it, we learn not just about one strange object, but about the full range of possibilities in that frozen frontier. A mission to this distant target is a conversation with the deepest past, a chance to read a chapter of our solar system's story that has been kept in perfect, cold storage since the beginning. It turns our collective curiosity into a trajectory and our questions into a destination waiting in the dark. The ultimate mystery of Varuna may be the question we have not yet learned to ask. After 24 specific puzzles, from its impossible lightness to its phantom atmosphere, we stand at the edge of a deeper unknown. Every time humanity has finally turned a sharp eye on a distant point of light, it has shattered our expectations. We thought the moon was a dry, dead world until we found water ice in its shadowed craters. We believed asteroids were simple rocks until we discovered they were rubble piles and active worlds. We imagined Pluto as a blurry snowball until New Horizons showed us a stunningly complex landscape of mountains, plains, and glaciers. History tells us that our first close look at any new world does not just answer old questions, it reveals entirely new categories of phenomena we never dreamed existed. So what paradigm-shattering reality awaits us at Varuna? Perhaps its dark shroud hides not just a strange geology, but a form of chemistry or physics that operates only in the perfect, ancient cold of such a fragile, spinning body. Maybe the interaction between its porous interior, its potential subsurface slush, and the constant rain of cosmic rays creates an organic laboratory unlike anything else in the solar system, a factory for complex molecules we have no name for. Or perhaps the greatest revelation will be one of profound simplicity, showing us that this dark world is the rule, not the exception, and that our bright, active Pluto is the true outlier in the frozen belt. The final and perhaps most humbling possibility is that our very categories of thought are insufficient. Our language of planets, moons, density, and spin may be too crude to capture what Varuna truly is. It might exist in a category all its own, a new class of celestial object that defies our current filing system. The greatest mystery, therefore, is not on Varuna. It is within us. It is the limit of our own imagination when faced with the boundless creativity of the cosmos. We have mapped 24 known unknowns. The adventure truly begins when we finally see this world clearly, and it shows us the 25th, the thing we did not know we did not know. That moment of stunned, wonderful confusion is the ultimate prize of exploration, the reason we keep looking into the dark. Varuna's deepest mystery is its place among its own kind. When we line it up beside the other major worlds of the Kuiper Belt, it stands apart not as a king or a typical citizen, but as a shadowy outlier, a black sheep in a family of strange siblings. Take Pluto, the vibrant and complex patriarch. Pluto has a dynamic atmosphere that waxes and wanes, a heart-shaped glacier of nitrogen ice, towering mountains of water ice, and a system of 5 moons. It is a world of astonishing geological diversity, a place where the distant sun's feeble light still drives real change. Varuna, by stark contrast, offers a featureless black silence. It hints at no atmosphere we can confirm, shows no surface detail, and travels in solitary silence. Where Pluto is a dynamic system, Varuna is a monochrome enigma. Then there is Eris, the current title holder for the most massive known dwarf planet. Eris is denser and brighter than Varuna, with a surface dominated by reflective methane ice that gives it an almost snowy sheen. It is a cold, distant mirror ball. Varuna's darkness is the photographic negative of that image, a world that absorbs light instead of flinging it back. Their densities tell opposing stories. Eris suggests a substantial rocky core, while Varuna's impossible lightness suggests a fragile, porous void. They are two extremes of the same belt, one defined by what it reflects, the other by what it consumes. Compare it to the tumbling cosmic football that is Haumea. Yes, they share that trait of rapid, dizzying rotation, but Haumea's spin has sculpted it into a uniform, crystalline ellipsoid and surrounded it with a family of fragments and 2 moons, the clear aftermath of a colossal impact. Varuna spins just as fast, yet it appears utterly alone, with no known family and a shape that remains hotly debated. Haumea's story is written in the debris around it. Varuna's story is locked inside, with no accompanying narrative in the space nearby. Even Makemake, the bright and seemingly featureless one, offers a contrast. Makemake's high reflectivity suggests a surface frequently refreshed by volatile ices, perhaps through seasonal frost migration. It is a world that manages its appearance. Varuna's unrelenting darkness suggests a surface that has been left to bake and blacken for eons, a stain that has set permanently. One is a world that wears a bright mask, the other seems to have absorbed its own identity into a permanent shadow. This comparative view reveals the true nature of the puzzle. Our attempts to classify the denizens of the Kuiper Belt create boxes, the complex ones like Pluto, the bright ice balls like Eris and Makemake, the fast-spinning families like Haumea. Varuna slips out of every box we try to put it in. It is not simply another variant, it is a categorical outlier. Its combination of profound darkness, startling lightness, solitary existence, and ambiguous shape does not neatly fit the origin stories we have crafted for its neighbors. It forces us to ask if our categories are too narrow, if the processes in the early solar system were even more varied and creative than we have dared to suppose. In a realm of frozen wonders, Varuna's greatest distinction may be its stubborn refusal to be anything but uniquely, mysteriously itself. From its impossible lightness to its phantom atmosphere, we have traced the edges of a profound cosmic silhouette. Varuna stands as a collection of contradictions, a world defined not by what we know, but by the glaring gaps in our understanding. Its very existence challenges the neat categories we try to impose on the solar system's frozen fringe. Is it a fragile rubble pile or a merged binary, a dormant relic or a world with a slow, cold pulse? The evidence points in multiple directions at once, leaving us with a portrait sketched in questions. This dark wanderer is more than just another distant object. It is a masterclass in cosmic mystery, reminding us that some of the universe's most compelling stories are written in whispers and shadows, in data that refuses to align and in light that reveals only a deeper darkness. Each of its 25 puzzles, from the spin that should tear it apart to the shroud that hides its face, is an invitation to look closer, to question our assumptions, and to embrace the thrilling uncertainty of exploration. So we turn the question to you as we close this journey into the dark. Which of Varuna's mysteries captures your imagination the most? Is it the secret of its impossible density, the ghost of its missing moon, or the tantalizing possibility of a hidden ocean beneath the tar-black crust? Share your thoughts in the comments below and let us know which cosmic puzzle you would unravel next. If you enjoyed this deep dive into the unexplained, be sure to subscribe for more journeys to the edge of our understanding. The universe is filled with stories waiting to be told, and the next great mystery is always just over the horizon. Until then, keep looking up.